Okay, welcome to the second part of our video lecture series on work, energy, and power. We are now on the second half of the second part of our video lecture series, and this would be on energy. Okay, so let us define first what is energy. Energy is defined as the capacity to do work. Now, try to notice the definition of our energy. It is defined in terms of the work, and the work here refers to the scientific work that was defined in our video lecture series of the first part of this video lecture series. Okay, so try to notice how the concept of energy was defined. It is the capacity to do work or the ability to do work. Now, when we talk about the ability or the capacity of doing something, it is either this capacity is present or this ability is present or not. So when we say that we have energy as the capacity to do work, this means that energy could be present and energy could be absent depending on the situation. So how is it that energy was defined as the capacity to do work or the ability to do work? So to illustrate this idea, let's take on a common example to illustrate this one, a bow and arrow. Okay, so what you see here is a person that is holding a bow and arrow. This is the bow, and this is the arrow. Now, try to notice the scenario wherein the bow and arrow is unstretched. It is unstretched. So, for example, this illustration here. Of course, if you're going to mount the arrow on your bow, so the relevant question is, does the string of the bow has the capacity to do work on the arrow so that the arrow would fly if the string of the bow is unstretched, meaning it is straight like this one? So the obvious answer to that is obviously the string of the bow has no ability in letting the arrow fly simply because it is unstretched. This means it is required for the bow and arrow to work. The what is required here is for the person to stretch the string of the bow and mount the arrow on the string so that the string would now gain this capacity to do work on the arrow so that the arrow would fly. In this example, we have illustrated that there is a presence and there is an absence of this ability to do work on the arrow. And this is when the string of the bow is stretched or unstretched. So when the string of the bow is unstretched, meaning it is simply going straight like straight here, then it would not have this ability to let the arrow fly. It is required for the bow and arrow to work for the person to stretch on the string and mount the arrow on the string so that the arrow would have this ability to do work on the arrow and the arrow would fly. This illustration illustrates that there is a presence and there is an absence of this ability to do work on the arrow, and we call this ability to do work on the arrow, which could be absent or which could be present. We call this energy. Now, so instead of saying that there is a presence or there is an absence of this ability to do work, we simply say that there is energy or there is a presence of energy, there is an absence of energy. So what is illustrated here is that in sequence, the person has to do work on the string, stretching the string so that the string would gain this ability to do work on the arrow, so that when the person releases the string and the arrow, the string would do work on the arrow, and the arrow would fly, and in turn, whatever target would the arrow hit, the arrow would also do work on that target. So what we see here is that it is being illustrated that the amount of energy can be passed on from the person to the string to the arrow to the target. So this also means that if you are able to pass on energy from one object to another, this means that energy could be transferred from one location to another. Okay, so let's move on with our discussion on energy. So energy, we have already established that energy could be present, it could be absent. It is the ability or the capacity to do work. Now, the release of energy does work, and doing work on something adds energy to it. Energy and work are actually equivalent concepts in physics. So energy is equivalent to work, not entirely work, but the capacity to do work. In the English system, the unit of energy is the pound foot. In the metric system, it is the Newton meter, which is also called the joule, indicating that work and energy have the same units because energy and work could be are simply equivalent to each other. By definition, 1 joule is the ability to exert a force of 1 newton over a distance of 1 meter. Now, energy is said to be a conservative quantity. What is meant by conservative here is that when something goes under a certain process, and that process involves a transfer of energy, that energy that is transferred could also be retrieved if you're going to reverse the process, and the retrieval of that energy does not dissipate or does not lessen the value of the energy that was transferred before. So when you transfer, for example, an amount of energy from object A to object B by doing work, you could also retrieve that amount of energy if you're going to reverse the process of transferring the energy from object B to object A. Okay, so this idea is known as the law of conservation of energy, and it states that energy cannot be created, energy cannot be destroyed. Energy can only be converted or transferred from one form to another. Just like what was illustrated earlier, that energy can be transferred from object A to object B in one form or another. It could be also transferred from object B to object A. Thus, energy is said to be conservative. So, for example, no, when Gohan here eats a certain an amount of food, and food is converted in the form of energy by the process of digestion, the amount of energy equivalent to the amount of food is transferred to bodily functions such as muscular functions, mental functions, and other bodily functions. So, for example, if the input energy is 100 joules, this 100 joules is transferred into different forms, but the amount does not change, so that when you add 35 with 40 with 25, that is still equal to 100 joules. Now, there are different forms of energy we call mechanical energy, and one of the many we actually have three forms of mechanical energy. One is the kinetic energy, another is the potential energy, and the third one is the rest energy. Each of this energy will be discussed later on, but I will now be discussing the rest energy. The rest energy is actually not presented here in this PowerPoint presentation, but I'll just be mentioning it here. The rest energy is the rest energy due to the mass of the given object. Kinetic energy is the energy possessed by an object due to its motion. So kinetic energy is actually dependent on the velocity of the given object, or the speed of a given object. For as long as the object is moving, it has kinetic energy. While potential energy is the type of energy that is dependent on the object's position, state, or shape. So example of potential energy is gravitational potential energy, which is dependent on height. It is the energy involved whenever you are going to raise, for example, a hammer, and eventually make use of that energy stored in the hammer to hit a nail, so that the nail would eventually pierce through wood or cement, and so on. So in order for the hammer to gain a certain amount of potential energy, the hammer should be raised. at a given height. So therefore, the height is the state or position of the object. It would not have gained any potential energy if the hammer was not raised to a certain position. Now, if kinetic energy is dependent on speed, potential energy is dependent on height or position or shape or state. Rest energy, on the other hand, is dependent on mass. By virtue of the mass of the object, the this equivalent amount of mass generates an equivalent amount of energy, as stated with the in the equation E equals mc square. If you're familiar with E equals mc square, this is the most famous equation of Albert Einstein, which indicates the mass energy equivalence. Okay, so unfortunately, it is not presented here in this a PowerPoint presentation, but I suggest that you research further on the mass energy equivalence of Albert Einstein. But this is simply called the E in the equation E equals mc square. E represents the rest energy, m is the mass, and c is the speed of light, and it is actually is squared in the equation E equal to mc square. Okay, so that is for the rest energy. Okay, so let's have kinetic energy. Kinetic energy is the energy, as mentioned earlier, is this energy of a body possessed by the body due to its motion. So the requirement for an object to have kinetic energy is that the energy should be moving. Okay, so example, suppose you throw a ball. Hence, you do work by getting the ball moving. You exert a force F over a distance d while you're holding the ball. The ball then has acquired some energy, and this form of energy is in the form of kinetic energy. So, indicating also that the work done by the person on moving the ball across the distance while the ball is still on the hand of the person is the work done on the ball, and this work done translates into the amount of kinetic energy gained by the ball. Now, once the ball was released in the hand of the person, the ball would have gained an amount of velocity or speed, and this translates that the ball would have gained an equivalent kinetic energy given by the person. So, throwing a ball gives kinetic energy on it. Now, for the working formula for the kinetic energy, we have K equals 1/2 mv square, where K is the kinetic energy given in joules, velocity is given by v in meter per second, and m is the mass of the object, which is expressed in the units kilograms. Okay, so let's take on one example. A 1,000 kilogram car is moving at a velocity of 30 meter per second. So what is its kinetic energy? So for this example, we have this is the same problem presented in the PowerPoint presentation. So we have the 1,000 kilogram car as the mass of the car. Substitute it in the given equation, 1/2 mv square times the speed or the velocity, 30 meter per second. So this is simply 30 squared. That gives you 900 times 1,000 divided by 2 gives you 450,000 joules of kinetic energy. Okay, so moving on. Let me introduce to you at this point the work energy theorem. Okay, so the work energy theorem states that the work done by the net force on a particle equals the change in the body's kinetic energy. This theorem also explains that when a body accelerates, the kinetic energy of a body will change. This is the basic idea that was presented earlier in the transfer of the work done by the person on the ball, as illustrated here. What is working here is the work energy theorem, which simply states that the work done by an object, causing the object to move from a certain distance, is being equated to the amount of kinetic energy gained by that object. So just like what is illustrated here, that the work done by the person in moving the ball across this distance translates into the amount of kinetic energy gained by the ball eventually once the ball was released by from the person's hand. So this is what is stated here in the work energy theorem. So How is the work energy theorem work? This is simply equal to the work done is equal to the change in kinetic energy of the object. So this is work equals delta K. So just like what is illustrated here, work is equal to delta K, or the change in kinetic energy, which is obviously computed by final value of the kinetic energy minus initial value. Okay, so the final value does not have any subscript. K sub 0 is your initial kinetic energy. Okay, so if the final kinetic energy is given by K sub 2 and the initial kinetic energy is given by K sub 1, and each of this kinetic energy is 1/2 mv square, having 1/2 m as the common term, we could actually bring that out from the grouping so that we end up with 1/2 m times v square v sub 2 square minus v sub 1 square. That is equivalent to the work done, which is equal to the change in kinetic energy. Okay, so m is obviously the mass of the object, v sub 1 is the initial velocity of the object, v sub 2 is the final velocity, kinetic energy 1 is the initial kinetic energy, and k sub 2 is the final kinetic energy. So let's take on an example for this problem. Okay, so what we see here in the PowerPoint presentation is the same as presented here in the document. Okay, a sled with a mass of 1,500 kilograms has an initial speed of 2 meters per second. So what is the speed of the sled after it moves 20 meters? What is the work done on if the work done on the sled is 14,700 joules of work? Okay, so since the work done is equal to the change in kinetic energy, which is given in the problem as 14,700 joules, we could actually equate 14,700 joules with the difference K minus K sub O, or final kinetic energy minus initial kinetic energy. So from here, what is being asked is the speed of the sled after it moves 20 meters. So that means we're looking for the speed that is within the formula of the final kinetic energy. So this means our strategy in solving for this problem is, first we need to compute for the final kinetic energy. So from here, W is equal to K minus K sub O. We could actually transpose negative K sub O to the side of W, making that positive, so that this becomes work plus K sub O. That is equal to K. Now, of course, the work done is given as 14,700 joules, plus the initial kinetic energy is given by 1/2 times 1,500 kilograms. This is the mass, times the initial speed, which is 2 meters per second. Now, of course, the result gives us 14,700 joules plus 3,000 joules. You could try this on in your own calculators. That gives us 17,700 joules. That is our final kinetic energy. Now, from our formula for the kinetic energy, if this is final, that is given as 1/2 m final velocity square. We solve now for the final velocity, that is given as you cross multiply 2 to the side of k, so that becomes 2k. You divide both sides by m, so that becomes 2k over m. Then you get the square root to extract your v, so that becomes square root of 2k over m. So substitute, this becomes square root of 2 times 17,700 joules over 1,500 kilograms. So that gives us 4.86 meter per second as the final speed of the object when the object went through the distance to 20 meters. Okay? Okay, so moving on. Let's move on now to the second type, or the third type of mechanical energy, which is the potential energy. This is already the third type. The first type was presented earlier as the rest energy. The second type is the kinetic energy, and the third type would be the potential energy. Okay, so potential energy is defined as the energy stored in an object due to its position, state, or shape. It is energy stored by virtue of position, by virtue of state, or by virtue of shape. That is why it is called potential energy. The word potential is usually being used in situations wherein you could actually hide something and eventually tap on it. So in the form of potential such as talent, no? Talent could be a potential uh, when we say that we someone has talent, we usually say that that person has potential. Okay, so the word potential is associated with something that is hidden or stored that we could eventually tap on, so that we could release that something that is hidden, such as talent or such as energy. Okay, so let's take on an example. Wounded up spring. This is read as wounded, as past tense to wind or wound. This is not this does not refer to wound, which refers to sugat, but this refers to the winding of the spring. Okay, when you wind up a spring and stretch the spring so that it would have an elastic potential energy, stretch bowstring. So these are examples actually for potential energy. You could store potential energy such as in springs, in bows and arrows, such as when I have illustrated to you in the bow and arrow illustration. So these are forms of potential energy. Particularly, we call this elastic potential energy. Also, in the example of the hammer and the nail, when you raise the hammer, you're actually moving the hammer against gravity. So this is an example of potential energy, particularly gravitational potential energy. Okay, so we have many forms of potential energy, such as elastic potential energy, gravitational potential energy. Another example is chemical potential energy. Energy stored in chemical reactions such as when you put Mentos on Coca-Cola or Coke. What happens to the Mentos is that it releases this chemical reaction. The chemical reaction is actually a form of released potential energy. Thus, chemical energy is a form of potential energy. So what is illustrated here are different forms of potential energy. So again, I'll be mentioning it. Different forms of potential energy. In this illustration, we have elastic potential energy, such as in springs and bow and arrow. Gravitational potential energy, such as in the hammer example, and chemical potential energy, such as in the example for Mentos and Coke. Also, it is worth noting that whenever you take on, for example, vitamins or medication, that the energy released from those pills are actually in the form of chemical potential energy. Okay, so but at this point we will be simply focusing on one type of potential energy, particularly the type of energy which is by virtue of gravity. So this is called gravitational potential energy, and this gravitational potential energy is represented by this symbol U, which has the form of mass times g times height. Try to notice that mass times g is actually the weight of the object by virtue of Newton's second law. M times g, mass times acceleration. This is actually the weight of the object. So this is basically a force. Force times height. Height is distance. So force times distance gives you work, and as we have illustrated earlier, work and energy are equivalent to each other. So therefore, if this is work, that is equivalent to an equivalent amount of energy in the form of the gravitational potential energy, simply because the force illustrated here is by the weight of the object. Okay, so U is equal to the gravitational potential energy, which is equal to the product of m times g times height. Okay, so m is the mass, g is the acceleration due to gravity, which is 9.8 meter per second square, h is height in meters, and u is equal to the potential energy in joules. Okay, so when a body changes the elevation with respect to the Earth's surface, the gravitational force or weight is doing work on the object. This work may be positive depending on the direction of the object, and this work is equal to the negative change in the body's potential energy. So as illustrated here, when the object is falling, so that falling meaning the object started with a higher elevation or higher height, moving to a lower elevation or lower height, what happens to the potential energy is that the potential energy actually decreases. So simply because the height is being lowered. Just like in the illustration, the lower the height, the lower the potential energy. The greater the height, the greater the potential energy. Okay, so since when the object falls, the object actually moves from a higher elevation to a lower elevation. So therefore, the system actually loses potential energy. So from a higher potential energy to a lower potential energy, and we usually associate this with a positive work done. So whenever work is positive in gravity, the potential energy actually decreases. Now, in the opposite sense, when the object is thrown upward, meaning that the object moves upward, the moving upward means that the object started with a lower elevation, ending up with a higher elevation. Going into a higher elevation means that the object increases in potential energy. So when the object increases in potential energy, the associated work done is actually negative. Why is it that the object is negative? Notice that the force of gravity is always downward, but when you throw an object upward, the distance is actually going upward. Therefore, the work done is negative, simply because force and distance are in opposite direction. While in the object that is falling, the force is positive simply because the force, which is downward, is in the same direction as the distance traveled by the object. So therefore, in conclusion, when the work done is positive in gravity, this is associated with a decrease in potential energy, and when the work done is negative, this is associated with a gain in potential energy. Oh, okay, so also take note that when an object falls, the kinetic energy of the object also increases. So we could also inject here an association between work and potential energy and kinetic energy. So when an object falls, the object actually speeds up. So therefore, there is an associated increase in the kinetic energy. While when the object is thrown upward, when the object rises, what happens to the object is that eventually the object slows down and momentarily stops when the object reaches its maximum height. So therefore, the pattern for the kinetic energy is that the kinetic energy actually decreases as the object goes when the object rises. So to make the conclusion complete, we could state the conclusion this way: when the work done is on the object, when the object falls, the work done is positive. It is associated with an increase in kinetic energy and a decrease in potential energy. When the object is thrown upward, so that the object rises, the work done by gravity is negative and is associated with a decrease in kinetic energy and an increase in potential energy. Okay, let's take on two sample problems. The same sample problems are the same problems that is presented here in this document. Okay, so what is the potential energy of an 800 kilogram elevator at the top of a building 380 meters above the street with respect to the ground, letter B, with respect to the top of the building? Okay, so um, with respect to the ground, the potential energy of the elevator when the object is on top of the building is actually this one. Okay, so with respect to the ground, from the ground to the top of the building, the height is actually 380 meters. So therefore, the potential energy of the elevator when it is on the top of the building is simply given by the product m times g times height is 2979200 joules of energy. Now, with respect to the top of the building, the meaning if you're going to put the reference of the reference from which you measure the height is when you put it on the top of the building, so that when you render that the reference position for the height is actually on the top of the building, and since the elevator is also on top, therefore the position in terms with respect to the top of the building is 0. So the potential energy of the elevator with respect to the top of the building is 0. Now for letter B, a 0.3 kilogram ball was dropped from the top of the building from a height of 300 meters. What is the work done when the ball is 30 meters from above the ground? And letter B, when the ball hits the ground. Okay, so the solution is U is equal to m times g times height, 0.3 kilograms times 9.8 times 30. That gives you 88.2 joules. Whereas when the ball hits the ground, the energy is equal to 0. Of course, the reference here is equal to, the reference for computing the energy is equal to 0. Is the ground. Now, earlier I have mentioned the work energy theorem, and that is summarized in what we call the law of energy conservation. Basically, what I have mentioned is summarized here. So you just go through with the notes here as part of your lecture notes. Okay, so lastly, the idea of power. Okay, so power is defined as the rate of work done or rate of energy transfer or energy conversion. The unit of work of power is the watt. Now, for the formula of power, power is said to be defined as the rate of work. When we say rate, we are actually referring to an amount divided by time. So power is the rate of doing work. So therefore, power is actually work divided by time. Or in essence, power could also be equal to force times the average velocity. Later on, I will be presenting to you how did it became force times average velocity when we do the sample problem. Okay. Okay, so let's have an example. When you do work on a box. For example, when you lift it using the time 5 seconds to lift the object with a work done of 100 joules. So that the power is simply work divided by time. So 100 joules over 5 seconds, that gives you 20 watts. Okay, so let's have this example. Okay, so each of the two jet engines in a Boeing 767 airliner develops a thrust, a forward force on the airplane of 197,000 newtons when the airplane is flying at 250 meter per second. So what horsepower does each engine develop? Okay, so this is the transition formula for for the formula presented earlier. Notice, power is work over time. We know that work is force times distance. If we rearrange the force, the quantities here, force and distance over time, we know distance over time is equal to the speed or simply the average value. Thus, power has also the form of force times the velocity or the speed. So we can use actually the second form in order to solve for this problem. So, okay, so we're given the force 197,000 newtons multiplied by 250 meter per second. So that gives us 4,925,000 or 4,949,250,000 watts. Now, for the conversion between watts and horsepower, for every 1 horsepower, we have 746 watts. So that would give us 66,018.77 horsepower. Okay, so this ends our lecture video series for work, power, and energy.